Hello students, this is Dr. P. Lakshmi Prasanna, the lecturer of the Social Welfare Degree College, Shamirpet. Today I am going to discuss about the Cauchy squares inequality. Okay, what is Cauchy squares inequality? Okay, what is the purpose of this Cauchy squares inequality? So, this is using for the joint probability function only. So, what is joint probability function? Two random variables x and y. X and y are the both are the joint probability distribution variables. Okay, x is the single variable, y is the another variable. If you are combining two variables, that is nothing but x and y, that is the joint distribution function of the two random variables. Okay, this Cauchy squares inequality is also helpful for the two random variable purpose only. So, that is x and y, and also it is the unknown values. Okay, x and y, that is the unknown random variables, and this joint distribution function of the two random variables purpose is in Cauchy squares inequality, the upper bound for the expected value of the product of x and y variables. Okay, what is Cauchy squares inequality? Expected value of x y whole square, x and y, the product of the two random variables. Okay, that is the upper bound. Okay, x square, it should less than or equal to the product of the each random variable, that is expected value of x square and expected value of y square. Okay, this is actually the Cauchy squares inequality purpose is only for the two joint distribution of the random variables of the upper bound of the product of the single each random variable, that is x and y. Okay, that is expected value of x square and expected value of y square. This inequality is also termed as one of the moment inequalities also. This Cauchy squares inequality is using for the two random variable purpose only. Okay, that equation we will see, that is expected value of x y whole square, it should less than or equal to expected value of x square into expected value of y square. Here we are taking some real valued function. Okay, that is z of t. T is the nothing but real value. Z of t equal to expected value of x plus ty whole square. Okay, the real value is the t, and x plus ty is whole square is should greater than or equal to 0 only. Okay, that is the all are should greater than or equal to 0. So, here we are considering let z of t equal to expected value of x plus ty whole square. So, here x is one random variable and y is the another random variable and t is the real value function. So, this t real value function is joining with the another random variable. Here the joint distribution function of the random variables are x and y. Okay, expected value of x plus ty whole square, it should greater than or equal to 0 for all real value of t. So, what is this expected value of x plus ty whole square? It is in the form of a plus b whole square. So, what is a plus b whole square? We know a square plus 2ab plus b square. So, we have to apply this a plus b whole square, that is x square plus 2ab plus b square, it should greater than or equal to 0. So, after expanding this a plus b whole square, we have to apply the expectation also. Okay, this Cauchy squares inequality is for the upper bound of the joint probability distribution function. Okay, this we are applying for the for three terms we are applying expectation. So, that is expected value of x square and plus expected value of y square, and where t is also real value function, that is the constant. So, wherever we have the constant, that is taking out of the expectation only, and 2 of t and e of x y. Okay. So, here this is looks like a quadratic function. So, what is quadratic function? Ax square plus bx plus c cx square. So like that this function is also looks like a quadratic function, that is z of t is a quadratic expression in t. Okay. So here we are comparing with this quadratic expression with this expansion. So how can we take a equal to expected value of y square and b equal to 2 into e a of x y, and c is nothing but another term. So after comparing this term, so this is the quadratic expression. What is quadratic expression of the discriminant of the expression? That is b square minus 4ac less than or equal to 0. So what is b square? This b, what is the b? Already we assumed that value. So that is the simplification. B square nothing but c, 2 into e of x whole square b square minus 4ac. A term is e of x square, c nothing but e of y square, that should greater than or less than or equal to 0. B square minus 4ac, it should less than or equal to 0. So here after 2 square nothing but 4 and 4 taking common, it should be 0, and then we will get some expansion, expected value of x y whole square less than or equal to expected value of x square and expected value of y square only. The joint function of the two random variables whole square, it should less than or equal to each individual product of the random variable, one x square and y square. So this is the Cauchy square inequality expansion. How can you solve this expansion? Through this quadratic expression of the discriminant of the expression. So then it is the Cauchy square inequality statement is expected value of x y whole square less than or equal to expected value of x square into expected value of y square only. So this is the result of the Cauchy square inequality. This purpose is only for why we are using when the joint probability function of x and y is unknown, then upper bound for expected value of the product of the x and y can be found by using Cauchy square inequality. When expected value of x square and expected value of y square are given. This inequality is also termed as one of the moment inequalities only. Yes, this joint probability function of only x and y, and it is unknown. So then upper bound for expected value of the product of x and y can be found by using Cauchy square inequality only. When means then expected value of x square and expected value of y square are given only. This inequality is also termed is one of the moment inequalities only. Okay. After studying this, we are understanding this Cauchy square inequality. Okay. So that statement is also follows that whole square, the joint function of the xy whole square, it should less than or equal to expected value of x square and expected value of y square. So in this statement we proved through this expansion, quadratic expression expansion we applied, and after this we solve this, we will get the expansion of this Cauchy square inequality. So this is the Cauchy square inequality statement. So according to that we have to prove the some exercise problem. So I am taking one of the example. So we will see whether it is possible or not, okay, whether we have to check out. So let x and y have the two random variables probability distribution. We have to verify the Cauchy square inequality. So 2 here 1 and 2, okay, this is marginal distribution function. Okay. So if you are adding this, we will get 1 only. So 1 by 8 plus 3 by 8 and here 2 by 4. So this is only for question. Okay, this is the one of the example. Okay, x and y, and we will see the marginal probability function x and y are given. See, first 1 and 2 of the x are values 4 by 8 and 2 by 4, and here y is 3 by 8 and y2 is 5 by 8. How it is? Oh, have you understood this? 1 plus 3 is nothing but how much? 1 plus 3 is 4. So, 4 by 8 and 2 here you see. So, that is 2 by 4. How it is? So, here see, this p of x means we have to add this values 1 and 2. Okay. 1 by 8 plus 3 by 8 how much? 4 by 8, that is. See here also 1 by 4 plus 1 by 4, 2 by 4, that is x terms, and y 1 by 8 plus 1 by 4, that is 3 by 8 only. 3 by 8 plus 1 by 4, that is 5 by 8. Okay. This is the marginal probability function x and y values. P of x is nothing but probability function. P of y is probability function of y. So, we have to check whether it is satisfied or not. Expected value of the product of x and y whole square equal less than or equal to each first term, x square term and y square term. So, first I am doing let expected value of x square. So, what is expected value of x square? So, how can you find the probability function, this expected value of x? What is general formula is summation of x into p of x only. So, here also expected value of x square nothing but that function. Summation is our as it is formula according to that probability distribution function. How in discrete case how can we write summation that x into p of x only. So, same thing here x square is there. So, summation x square into p of x. Okay. So, what is x square? X square nothing but we have the function. So, what is x square? See, x square nothing but this 1 and 2 values are there. So, 1 square into, and what is our p of x? This first one 4 by 8. So, see 4 by 8 plus 2 square into 2 by 4. So, like that. So, okay, after applying this formula we will get 5 by 2. Similarly, you apply expected value of y square. What is that function? Summation y square into that function. Same you apply the y square function. What is 1 square into that p of y function and 2 square in that p of y function. So, after getting we will get 5 by 2 is the first function and second function is 23 by 8. And this is only for individual x square and y square. Okay. Then joint probability function. Joint meant nothing but combination of the x and y, combining. So, that is x and y both. X and y nothing but how can we do? See here, this one 1 into 1 by 8 plus 1 into 2 into 3 by 8 plus 2 into 1 by 4 plus 2 into 1 by 4. So, same thing here we are done in the joint distribution function of x and y. So, after simplification we will get this 19 by 8. Okay. This xy is the joint function. This function it should less than or not for this x square and y square. Yes. What is x square? Already this x square function is 5 by 2 and y square is more 23 by 8. Okay. It is higher than this xy. So, obviously it is satisfied. Cauchy square inequality. See, expected value of xy whole square it should less than or equal to individual function x square and y square. So, it is will satisfy the Cauchy square inequality. Why? Because this is the when the joint probability function of x and y is unknown, then the upper bound for unexpected expected value of the product of x and y can be found by using this Cauchy square inequality when expected value of x square and expected value of y square are given. So, this inequality is also termed one of the moment inequalities only. So, the product term is whole square is should less than or equal to individual term x square and y square. So, this example is satisfied. So, we will see in another example for continuous series. Okay. So, see that random variables x and y, the joint probability density function. So, the joint nothing but we know Okay, density function, function nothing but it is the continuous series. Okay, continuous series nothing but f of x comma y. Okay, see there in the first example problem is the probability mass function only. Now we are coming to density function. So that is e of minus x plus y, it should x greater than or equal to 0, y greater than or equal to 0. So all should positive only, means all are non-negative only. Okay, we have to verify the Cauchy squares inequality. What verification? It should less than or equal to that function. Expected value of xy whole square is less than or equal to expected value of x square into expected value of y square. So first we have to find the marginal probability density function of x and y. Okay. So f of x equal to, how can we write the marginal probability density function? This is the formula, f of x equal to integration y f of x comma y dy. Okay. So that function you write. Okay, what is our function? E of minus x plus y. Okay. So what is this limits? It should greater than or equal to 0. Means what is that? Actually minus infinity to plus infinity is our limits. General limits are minus infinity to plus infinity. Here we are given the x greater than or equal to 0, y greater than or equal to 0. Then what we will get? It will start from 0 to lower limit is, lower bound is 0. Okay, upper bound is infinity. So that function is e of minus x plus y dy. Okay. So here y function is there. So only in integration part we have to consider only y function only. So that is why whatever we have the another terms we have to taking outside of the integration. So that is why e power minus x we are writing outside of the integration. Okay. Remaining terms are within the integration only. So integration 0 to infinity e power minus y dy. So what is integration of the e power minus y? So that is, see here, e power minus y by minus 1. After applying the lower bound and upper bound. So upper bound minus upper limit minus lower limit. So that is 0 minus 1. So that is what we will get, minus into minus plus e power minus x. It is the only for marginal probability density function of only for the y only. Okay. Next, since x and y are the symmetrical, then we get f of y, all symmetrical nothing but same. So that is why f of x what we will get, e power minus x, then obviously we will get the f of y equal to e power minus y only. Okay. And next we have to take the expected value of x square. So next expected value of x square, how can we find the probability mass function in discrete case? So same thing, integration that function into f of x dx. Okay. So what is our function? Only x square only. So what is our f of x function? E power minus x. E power minus x is our function. So x square into e power minus x. So x square into e power, that is in the form of, what is in the form of x square into e power minus x? That is in the form of uv form. So what is uv form? We know the formula. Okay. So according to that uv rule we are applying this expansion. Okay. After differentiation we will get this expansion. So after applying we will get 2. Okay. Minus into minus plus, so 2. Next, similarly expected value of x square we are getting 2. So similarly we will get the expected value of y square is also 2 only. Next, the joint probability distribution function of the variables. The joint nothing but expected value of x and y. So double integration and that function into f of x comma y dx into dy. Okay, that is the formula for the joint probability distribution function of the probability density function. So what is the probability density function? This is 0 to infinity. These are the limits because they are given limits, non-negative functions, x greater than or equal to 0 and y greater than or equal to 0. So it is 0 to infinity and 0 to infinity, and xy and that function. What is that function? e power minus x plus y dx into dy. Okay. Then separate the terms, x terms we have to separate and y terms we have to separate with the integration only. Okay. After separating this, we will get this integration x into e power minus x dx, that is separation of the x terms only, and y terms integration y into e power minus y dy. So, here also we have to apply uv rule, integration of uv rule. Okay. So, u v dash, okay, here see, and this one. So, similarly here also y into ey. Okay. So, after applying this uv rule, then upper limit and lower limit also applying, then we will get the 1 only. Okay. So, the joint distribution function will get only 1 and individual function of the expected value of x square is 1 and expected value of y square 2, expected value of x square is 2 and expected value of y square is 2. So, 1 square is less than or equal to 4. Yes, this is obviously correct. 1 is less than or equal to 4 only. So, here also Cauchy squares inequality satisfied for probability density function also, and also it will satisfied for the probability mass function also. Why this will be satisfied? Because we are taken the cases when the joint probability function of the x and y is unknown, then the upper bound for the expected value of the product of the x and y can be found using Cauchy squares inequality when expected value of x square and expected value of y square are given. This inequality is also termed is one of the inequalities only. So, this random variables are very helpful in this finding this Cauchy squares inequality. This expansion is will less than or equal to that product of the each square terms of the random variable only, because this is the real valued function. Okay. Here we are defining different type of terms and for real value we are considering only t only. Just we are taken some expansion of that variables, that is different type of, for solving this this expansion of this variables. So, this is possible for this this Cauchy squares inequality for probability distribution function, density function and probability mass function also. This is for probability mass function, we are marginal probability function, that is the case we satisfied that expected value of x square is expected value of xy whole square is less than or equal to expected value of x square into expected value of y square, and it is also satisfied for the two random variables have the joint probability density function, that is expected value of f of xy. The joint means the two random variables, that is f of x comma y, that is two joint distribution of the variables is also satisfied for this Cauchy squares inequality. So, here the Cauchy squares inequality is helpful for the only for lower bound and when the joint probability function of x and y is unknown, then upper bound for expected value of the product of x and y. Okay. So, what is that? Here all are should non-negative only, x is non-negative, that means x is greater than or equal to 0 and y also non-negative, that means y is also greater than or equal to 0. These are all found can be when expected value of x square and when expected value of y square is given only. Okay. These are all for the joint distribution function and product of the individual squaring terms, that is upper bound for the expected value of the product of the each and every variable, two joint random variables only. Okay. This inequality is for the movement purpose also we are using. So, this is only for the useful only for the in probability of mass function, in probability density function also. it is solving for the probability density function of the Cauchy-Schwarz inequality is satisfied, and in probability mass function of the discrete case also Cauchy-Schwarz inequality is satisfied. Whenever it is not satisfied, then we have to check why it is not possible, where it is not it is not less than or equal to some other conditions. Okay, here Cauchy-Schwarz inequality is actually summary is nothing but in this chapter actually inequalities are to find the limits of the curl Pearson coefficient of the correlation, and also show that for the distribution of the coefficient of kurtosis and is greater than the coefficient of skewness beta 1. Why it is beta 1 beta 2? Beta 1 is nothing but coefficient of the skewness, beta 2 nothing but coefficient of the kurtosis. And moment purpose also we are using this Cauchy-Schwarz inequality. What is beta 1? Beta 1 nothing but mu 3 square by mu 2 cube. Okay, that is moment purpose. And what is about kurtosis? This is the mu 4 by mu 2 square. So that is why here the curl Pearson's coefficient of correlation, and also to show that for a distribution of coefficient of kurtosis beta 2 is greater than coefficient of skewness beta 1. Okay. Actually we have to verify in remaining some examples are also there. This Cauchy-Schwarz inequality for the joint probability density function of x and y, it is possible or not. So x plus y they given, and 0 less than or equal to x less than or equal to 1. In some these are the limits 0 to 1 for x variable and 0 to 1 for the y variable. Okay, this is the one of the example. We have to check the model answer questions, and some questions are given for this expansion only. Actually in this chapter Cauchy-Schwarz inequality, in this concept actually different type of applications here also we have to use this inequality to find the limits of the curl Pearson coefficient. What is curl Pearson coefficient of correlation? Limits, these are all limits are only -1 to +1. Okay. What is correlation? It is the relation between any two random variables only, that is x and y only. Okay. So this Cauchy-Schwarz inequality is also and it is useful for the inequality to find the limits of the curl Pearson's coefficient of the correlation. So what is curl Pearson's coefficient of correlation? R equal to covariance of xy by sigma x into sigma y. There also we are using two random variables only. In Cauchy-Schwarz inequality also we have the two random variables, the joint probability distribution function of the random variables. Okay. And in this Cauchy-Schwarz inequality that expression is also that expected value of xy whole square is less than or equal to expected value of x square into expected value of y square. Here only we are using two random variables only. Okay. Same thing here also, the curl Pearson. Why? Because we are taking this curl Pearson means this is Cauchy-Schwarz inequality, and its application we use the inequality to find the limits of the curl Pearson correlation of the correlation. Okay, these limits are also what is that? R equal to covariance of xy divided by sigma x into sigma y. Covariance, that means joint, that is x and y, the joint probability function. Okay, so x and y is also joint probability distribution function. So here in curl Pearson's correlation also covariance of xy. So two variables only, and sigma x, sigma y. So individual random variables x and y. So that's why we have to apply this application also. We can take this, we use this inequality to find the curl Pearson coefficient of correlation. Okay. And we also show that for the distribution of the coefficient of kurtosis also. Kurtosis is beta 2 is greater than coefficient of skewness. Okay. Why beta 2 is greater than? Because that mu 4 by mu 2 square. Mu 4 is greater than the skewness of coefficient of skewness only, because skewness is only for mu 3 square by mu 2 cube only. Kurtosis is mu 4 by mu 2 square. So, obviously kurtosis beta 2 is greater than the coefficient of skewness. Okay. This distribution of the coefficient of kurtosis beta 2, this is also based on the only central movements only. Okay. And coefficient of skewness is also, it is based on the coefficient of the this central movements only, that is mu 3 square by mu 2 cube. Okay. Here mu 4 by mu 2 square. So, mu 4 is higher. So, that is why beta 2 is greater than coefficient of skewness beta 1. Okay. This is about the Cauchy squares inequality, and application purpose is also Cauchy squares inequality we have to apply in mathematical field, and we have to use in financial mathematics, and we have to apply in different types of this branching process in statistical inference. Okay. We are applying in many fields also this Cauchy squares inequality. Okay. Thank you.